Welcome to Module 5 on Detailed Project Example 2, ABC Decision Process with Negative ABC Decision. We're pleased to again welcome our speaker, Mike Culmo, Chief Bridge Engineer with CHA Consulting, Inc. Mike?
Thank you, Mary Lou. We'll move on to the next example. As we said before, people routinely tell us at the ABC UTC they want to see detailed project examples for ABC, and here's another one. So we'll go through a decision process for another project in Connecticut. This is an actual project that was actually built. So this is a project that was actually designed by our firm, so I know a little bit more about this than I do about the final design of the other bridge, but we'll go through this example. And there's another one located in eastern Connecticut. Again, Connecticut's a very small state, so but this is now in the northeast corner near the Massachusetts and Rhode Island border. Those of you who don't know the area that well, in New England's a very small condensed area with lots of people and lots of old bridges, which is why we do a lot of ABC, because we're dealing with lots of traffic and replacing existing bridges. And I like to say replacing a bridge with traffic is like changing the oil in your car with the motor still running. It's very difficult. So what we like to do with ABC is shut the motor off and change the oil quickly and get it running again. So this is the kind of thing that we deal with every day, and this is why ABC is an important part of the Connecticut DOT bridge program. So this bridge is located in eastern Connecticut, town of Killingly. It's a fairly rural section of Connecticut. I-395, the same interstate we spoke about before, over a local road called Tracy Road. Zooming in a little closer, this is in this photo, this is the border with Massachusetts, this is the border with Rhode Island, and the bridge is located here on Route 385 over a local road near the town of Putnam, Connecticut, which is a fairly populated area for rural northeast Connecticut. We refer to this part of Connecticut as the quiet corner for a good reason. It tends to have lower traffic volumes and more rural communities, farming communities, and such. But near this particular bridge, though, the bridge is located right here. Tracy Road is right there. And we're talking that we have an industrial park. This town has built an industrial park nearby. And we have things like a heavy industrial. This is a trucking company, I believe. And here are several manufacturing buildings over here. So there's actually a power plant located right here. It's a natural gas-fired power plant. However, most of this traffic doesn't take Tracy Road. Most of this traffic is getting on the interstate. But it does affect the ADT of the roadway on the bridge. The bridge goes over Tracy Road. Important thing to note about this project, it only involved the replacement of the northbound structure. For some reason, the southbound structure is not in as bad a condition. Maybe at some point in the future, we'll replace the southbound structure, but this project really just involved the replacement of the northbound structure of I-395 over Tracy Road. Zooming in a little closer on the bridge, the traffic volumes are fairly low on 395 in this area. However, you might say, wow, look, Mike, there's 3 lanes of traffic on this bridge. It must be a high ADT bridge. The reality is we're fairly close to the acceleration lane from the on-ramp for the interchange just to the south of the bridge. So this particular bridge has a climbing lane or an acceleration lane that goes across. So the third lane is not necessarily there for ADT. It's really there for the acceleration of vehicles coming up the highway. Tracy Road down below is a 2-lane road with a sidewalk. Again, it's a rural road. There's not a lot going on directly adjacent to the bridge. We have a large grass median. You'll notice the bridge is the 3-span bridge. You can see the joints at the piers and the abutments on this particular bridge. Elevation of the bridge. This is now a pre-stressed concrete ash-to girder bridge built in the late 60s, early 70s, if my recollection is correct. Looks like a pretty nice bridge, and it is a very nice bridge. However, and now we all, as bridge engineers, we all debate whether or not a concrete bridge is more durable than a steel bridge. And the answer is, if you have leaking deck joints, it almost doesn't matter whether it's a concrete beam or a steel beam, you could have problems. And this is a great example. You can see this pier has had a number of patches done on it already. And routinely our contractors, when they patch piers, it's due to insufficient cover of the concrete. So when they patch it, they increase the cover over the patch. So you get these funky looking patches that stick out. It's the way we do things in Connecticut. But it's a 3-span bridge with shoulder piers and abutments perched on top of the slopes underneath the bridge. Again, a plan view of the existing bridge. These are taken from the original plans, showing the arrangement of 3 lanes on the bridge. Again, 1 is an acceleration lane and 2 of them are the interstate. lanes, elevation of the bridge showing fairly standard framing and fairly standard geometry with a skew of approximately 45 degrees. Cross section of the bridge, again, this is very typical construction, showing astrogirders with a cast-in-place concrete deck. This is the shot from the original plans. These are Astro Type 4 girders, very common, still in use today, although nowadays we go more to bulb T girders. But your standard conventional composite bridge with Astro girders. See, the original bridge had actually was built with a bituminous concrete wearing surface and a membrane waterproofing. And this is with what we call woven glass fabric, which is a fairly high, a very high quality membrane that was built in the 1960s, going back as far as the 60s. We have found that bridges built with these waterproofing systems perform very well. However, we have joints on this bridge, and keep that in mind. The bridge joints are problematic. This is where we're going to see problems on this bridge. One of the problems with it, because of the astrogirders, the original designer decided to zigzag the joints at the end of the bridge. A very unusual joint configuration brought on by the skew of the structure. So you have this zigzag joint, which you can just imagine, how the heck can I put a bridge joint that won't leak with zigzag joints? And the answer is you can't, and they leak, and that's a problem. So again, leakage is a big issue with any bridge, whether it's steel or concrete. So I'm not here to badmouth concrete at all. I'm here to badmouth bridge joints, or I should say, inadequate bridge joints. And here's a photo underneath the bridge. You can see the bridge looks in pretty good shape. However, look, we got a post here. This beam has actually been posted up, not load posted, but posted up, meaning supported by a post, because of significant deterioration at the end of this beam. Basically, the last 2 feet of the beam were in terrible condition, and there was more than one beam that had this situation. So just a good example where even if you have concrete beams, if you have leaking deck joints, you can see the staining on the pier. These joints have just been leaking for years and years and years, leading to significant deterioration downstairs. So what was the project scope? Initially, it was a rehabilitation. The plan was to eliminate the joints and install link slabs. Sounds like a good idea. Repair the beam ends. Pretty tricky, but we felt we can come up with a repair to fix these beam ends. The problem with it is once you removed enough deck to install a link slab, you ended up taking about 20% of the deck, 20 to 25% of the deck had to come out just to open up the deck enough to build the link slabs. Then you had to repair the beam ends. Then you had to patch the substructure. And looking at life cycle costs, the answer was rehabilitation didn't seem to make an awful lot of sense because the rehabilitation cost was approaching the replacement cost. So the idea was it was rescoped as a full replacement using a newer technology. And the idea here was to use GRS IBS and convert the bridge from a 3-span bridge to a single-span bridge. So by doing this, we do a couple things. One, we have less substructure to maintain in the future. Two, we have less superstructure to maintain in the future. So we reduce the overall size of the bridge, which also reduces the cost of the bridge because now we're building a smaller footprint structure. And we actually open up the span by eliminating the shoulder piers, and we actually widen the road down below. So we're actually coming up with a lower cost first cost bridge. We're coming up with a lower cost long-term bridge. And we're using this new technology called GRS IBS. Now, for those of you who are not familiar with GRS IBS, when I first saw this, I kind of scratched my head. I wasn't quite sure. This was developed by Federal Highway Administration. I give them all the credit. It's a very simple structure that works very well. And the concept is we're using layers of geosynthetic reinforced soil to support a spread footing. The bridge is integral with the spread footing. And then the backfill behind the end of the bridge is a reinforced approach slab, or approach, you should say. They call it integrated approach. So the way this thing's actually, the really cool feature about this is the way they handle thermal movement, expansion and contraction, is it's not like an integral abutment bridge where the bridge is pushing against the soil. In a GRS IBS bridge, the entire abutment is flexing and moving with the superstructure. So you end up with no bearings, no approach slab, no joint at the end of the bridge, and these things have been proven to be very durable and they perform really well. So, and the best part is they're very inexpensive to build. So it's a fairly somewhat of an experimental project, one of the first GRS ABS bridges built in Connecticut. There are more being built or have been built and more planned, but just a little primer there on GRS ABS. I'll get off my sales pitch here, but it's just another form of ABC that we decided to incorporate in the project in the design, regardless of whether or not we used ABC. So the non-ABC option was stage construction. And the bridge being a 3-lane bridge, we had enough width to maintain 2 lanes in one stage, but then in the second stage, we had to go to a single lane of traffic, which is something that we had to deal with. So we'll get into the calculations in a minute, but that was the proposal of staging 2 lanes in stage 1, 1 lane in stage 2. So as far as the ABC option is to close the interstate completely in detour traffic and go and build the GRS-ABS bridge and then replace the superstructure with modular deck beams, as we discussed before. Construction time was estimated at 12 months, and the closure period would be 7 days to replace the superstructure. The idea would be is that we would build the GRS-ABS abutment. The majority of it could be built underneath the existing bridge before we did any closures up on the interstate, and then we can limit the construction to 7 days to replace the superstructure. So let's look at the detour. Let's look at what happens. So here's the project site. I've turned north now is to the left. This is the project site. Traffic is running north here. So we have the detour traffic getting off the highway, taking these state routes to go around the site and back onto the interstate. Approximately, I think I'll get to it in a minute, but I think it's 4.5 mile detour. So the segment length for segment 1, again, we're breaking the segment up into pieces. The first segment is off the ramp in this first little segment to get to this route here. This is it's called Attawaugan Crossing is the name of the road. It's a state highway with 2 lanes, speed limit of 30 miles per hour. This segment's 0.3 miles, 2-lane road, 1 traffic signal. So we go, now you're all becoming familiar with these details, but we'll go through it again. 0.3 miles, 30 miles per hour, congestion factor 1.5. Let's look at that. So at the bridge, it's a limited access highway at the bridge. We're detouring limited access highway traffic, but our ADT is fairly low. So we're dealing with, and now our detour segment is between 0.5 mile and 2 miles. Or actually, I got the wrong circle. It's down here. It's less than 0.5 mile. 1.5 is the answer for the congestion factor. I apologize for that error. The second segment is pretty standard 2-lane rural highway. So we just make it as 1 segment. Here's a photo of the segment, 2-lane highway, speed limit of 40 miles per hour, 3.6 miles with 2 traffic signals. So 3.6 miles, it's a longer segment length. ADT is higher, fairly high here. I might have skipped over the ADT, but it fell into this category of greater than 8,000 vehicles per lane. And we get a congestion factor of 2 for this. So we get a segment duration of 10.8 minutes. So total delay, when we throw in the 3 traffic signals, we get a delay of 14.7 minutes for the traffic using this detour. Now we need to look at the detour under the bridge. So here's Tracy Road underneath. We're looking at a detour from this point to this point. For cars were, if they were trying to take this road, they would have to go this way, as opposed to the great discussion we had before about how many cars go from one side of the bridge to the other. The answer is very few, but this is a more realistic approach looking at a detour, what a typical car would go through. Again, segment 1 is Attawaugan Crossing, again, 30 miles per hour, 0.6 of a mile, the same as before. The difference is we have lower ADT, and the condition at the bridge is a non-limited access highway with low ADT. So we have a congestion factor of only 1 for this case. Segment 2 is this little section right here, 0.2 miles, 40 miles per hour, 1 traffic signal. Only 0.3 minutes to go through this segment. It's only 0.2 of a mile. Segment 3 is Country Club Road. This actually is a local road. We normally wouldn't detour it on a local road, but we'll just say for the sake of this hypothetical, which the town was okay with a detour, or we might say this is what typical people would take because they know the area. 0.9 miles, 2-lane road, 25 miles per hour with 1 stop sign. Congestion factor goes up to 1.25, 2.7 minutes to traverse this. Now, one thing you could do, I didn't actually talk about this, but you could easily do this. These 2 segments are used both by the local traffic and the 395 traffic. So you could very well look at those 2, combine those 2, and get the segment length for 395 and add those 2 together and analyze these segments together. For this example, I didn't do it because you'll see why, because the answer is going to be we're not going to recommend closing these roads. So the total detour for the Tracy Road detour is 8.2 minutes. So let's look at the calculations. So now we're looking at, I'm sorry, we're looking at the option where we don't close the highway, stage construction, and we're going to go with stage one with 2 lanes of traffic and stage 2 with 1 lane of traffic. So this is the non-ABC option of keeping the highway open. Stage 1, by inspection, our ADT is fairly low, and we have 2 lanes of traffic in each direction. So we have actually the peak hourly volume is 1,600. So in stage 1 with 2 lanes of traffic at 1,600, by inspection, we know there's no delay. So we're just going to look at the heavy commute period for stage 2, where we have 1,600 vehicles per hour traveling on 1 lane in stage 2. So we have a delay of 6 minutes because we're above the 1,400 threshold. ADT is approximately 9,600 vehicles. It's a light traffic region, so we're going to go with a 1 hour peak, and we calculate 9,599 vehicle minutes. So we assume there are 2 peak periods in the morning and the afternoon. So those are the 2 periods, but off peak, our calculations showed that it was 0. And then we have a total delay, a weighted average delay time of 1.6 minutes. So let's look at the analysis of I-395 with regard to conventional construction with 2 stages versus ABC with a full closure and a detour. So with 2 stages of construction, again, stage 1 is not a problem. Stage 2 will have delays. We're estimating 75 days of construction to build, to close the road, tear down the old superstructure, finish building the upper half of the GRS abutment, and then installing the superstructure and backfilling. We estimated 75 days. There's a 1.6 minute average delay time, which we just calculated for 75 days. For ABC, we're going to close the bridge and use a 14.7 minute detour. And we're assuming that could be done in, I'm sorry, the 75 days of construction was in stages, but with ABC, we feel we could build in 7 days to build the superstructure and get it back open again. So as far as Tracy Road downstairs, the delay, only 3,000 vehicles per day. So delay time is, for conventional construction, we're assuming a 6-second average delay just due to reduced traffic speed through the work zone for 18 months. And then for ABC, 8-minute detour for 7 days, based on the calcs we did before. So the results of this tells us that the user reduction for ABC is actually a 13% reduction in ABC. In the world of these calculations, it's pretty much a wash. ABC and conventional construction are about the same. Let's take a look at costs. Again, we'll work our way through the matrix and go through all the numbers. This bridge also had a price of $5 million. Just a coincidence that they came out that way. As far as construction engineering and inspection costs, $5,000 a month for the field office. This one is $40,000 a month for CE&I staff. Would probably be 2 staff, both combining field office and main office staff. So the total cost per month is $45,000. The premium for ABC on this particular job, prefabricated, I should say, modular deck beams are fairly straightforward ABC process. Prices tend to be a little lower because there's not as complex, so we use 15% premium, and we're estimating we can only save 6 months with ABC. So with 6 months savings, we look at temporary barriers for stage construction. We estimate $75,000 for this bridge to do the 2 stages. Let's look at the cost analysis conclusion. The premium for ABC was $750,000. The savings with construction engineering and inspection was only $270,000. The traffic management with ABC, $75,000. Therefore, the net cost, ABC is $400,000 more expensive than conventional construction. So it's an 8% increase in construction cost to go to ABC. So let's recap a little bit. We have a project where the user impact is pretty much a wash between ABC and conventional construction. However, ABC is probably going to cost more. So let's see how that impacts the scoring. So we walk through our scoring calculations. The average daily traffic is fairly low, so we're going to use it at 2. This is combined traffic above and below the bridge. We're looking at between 10 and 40,000 vehicles. The user reduction, we get a score of 1 because it actually, it was a very minimal savings of about 13%. So the spreadsheet automatically enters 1 for the user reduction percentage. For bridge location, it's a rural bridge near a town center. So we give it a 1. It's not a highly congested area. Use the typical details. It's a skewed bridge similar to our previous example bridge. It's skewed at 45 degrees, so it's not totally simple, but the geometry is pretty straightforward. So we'll give it a 4. Work zone geometry, like their previous example, was an average project duration with average geometry and flow, so we gave that a 3. Site conditions, we gave it a 3. Minor limitations, but nothing major with downstairs. We have some utilities to deal with downstairs, but nothing over the top complicated. And no utilities on the bridge. And as before, we don't have railroads, we don't have water, and we don't have waterways. So we get 0s for those. So what's going to come out of this? What's the matrix going to tell us? We have I'm going to recap again. We have a project where the user impacts for ABC and conventional construction are pretty much a wash. But remember, the cost of ABC was probably going to be higher in this bridge than conventional construction. So the cost analysis, it was 8% was the increase for ABC. So that gives you a value of 3 for the cost analysis. So what do we get? Kind of what we thought. We knew this was kind of a wash from a project. It probably could go ABC, probably could go conventional construction, but probably because of the cost. And again, as Tim mentioned before, we're using a cost factor, a weight factor of 30 for right here, 30 for cost. So that's playing into this decision here, where we're getting a score of 44 out of 100, which says do not consider ABC. You could make a case to use ABC here very easily because we're close enough to 50. But the reality is, being a rural bridge in a rural community with not a lot of traffic on either road, and these detours were not the most desirable detours in the world, especially for the local community, that ABC probably didn't make any sense here. I shouldn't say that. It made some sense. It didn't rise to the level of making a decision to go with ABC. However, we want to use GRS-IBS is considered an ABC method. And why is that so? Because GRS-IBS bridges can be built very quickly, and also they can be built underneath existing structures fairly easily. Contractor was able to build, and these photos show on the left, shows the beginnings of the GRS-IBS footing going in, which is essentially a reinforced soil footing. It's not a concrete footing. That can be done with simple plate compactors. Very easy work, not a lot of big equipment. Once you start building the bridge, we're using blocks here that can be installed by hand, so we're not looking at heavy equipment. So we could build this entire abutment. I should say a majority of this abutment can be built underneath the existing bridge before we start closing the bridge upstairs and going to stage construction. So that is a form of ABC. It's an ABC method being applied to a non-ABC project. So we're building as much of the structure offline before we start impacting traffic. One thing you'll notice about this GRS-IBS bridge, a lot of GRS bridges are built with dry cast block. Connecticut DOT has made a decision to go to a higher quality wet cast block. So these are actually precast concrete blocks that are about 12 inches wide by 8 inches tall. They're small blocks, and they have a form liner to make them look like stone. And you can see from the photos I'll show you, they're very attractive looking blocks. And again, this is all built with small equipment under the bridge with very little rebar. In fact, there's virtually no rebar in these abutments, so they're super durable because there's nothing to corrode. So here's a shot of the completed bridge. I love this bridge. This is one of the more attractive bridges I think we've seen built. As far as the superstructure, we went from concrete to steel, not because we hate concrete. Don't get me wrong on here. It had to do with we increased the span about 20 feet. We wanted to keep the clearance as high as possible. And the steel girders allowed us to get more vertical clearance than an equivalent bulb T girder. So it was a case of geometrics and clearance was the reason to go to steel. Connecticut does build quite a few steel bridges. We actually aim to get about 50% steel, 50% precast or pre-stressed concrete. This particular bridge made sense to go to steel. So it's a weathering steel bridge. With GRS-IBS, we have no approach slabs, we have no bearings, we have no joints in the bridge. It's a simple saw and seal joint at the top. No approach slabs, which definitely reduce cost. So these are very cost-effective structures. I'm giving kudos to Federal Highway for their work on this technology. The Connecticut DOT went with the wet cast block instead of dry cast block for more improved durability. Interestingly, we built a number of these bridges in Connecticut, and my understanding, the district construction office had been getting phone calls and emails, people were complaining that we were wasting taxpayer dollars building these stone bridges on these interstate highway bridges, that we should be building boring concrete. Nothing against concrete, but we were building these really fancy bridges. And the reality is these bridges are significantly less expensive than a cast in place concrete structure. They're really a cool technology. It's an ABC technology that is included in the 2018 ABC guide specifications for ABC. So we consider this an ABC method. And so here's a case where we applied ABC prefabrication technologies to a non-ABC project and had a successful outcome. So with that, I'm going to leave that photo back up instead of the thank you. That concludes this presentation. I'll be happy to answer any questions you might have at this point. Looks like we're about 5 minutes early.
Yeah, thank you, Mike. Again, very informative presentation. We'll now begin the Q&A session for Module 5. Paul will be assisted by Ahmed Abu Hawash, Chief Structural Engineer with the Iowa DOT. Paul?
Okay, thank you, Mary Lou. And thank you, Mike. That is a real pretty looking bridge. We have a couple questions. Let's maybe, first of all, why was the ABC cost higher for this project when compared to the other example?
Yeah, I think the key thing is the amount of time that we were saving. This particular project, with the fact that we could build the GRS IBS abutment underneath the existing bridge for both the ABC option and the non-ABC option, it took an awful lot of the construction off the critical path. And therefore, the time savings for ABC was only, I forget the number I had, it was a couple slides back, was I think 5 months or 7 months.
7 months.
Was that 10?
I think 7 months.
7. Versus the other project, it was 15 months. So the real savings here was the fact that the real difference was the previous project saved more time in construction, thereby reducing the overall project cost by reducing the construction, engineering, and inspection costs. So here we had the ABC project wasn't that much faster than conventional construction, which is why we could not overcome the additional ABC cost with savings in construction management. So that's the primary reason why this kind of went that way. And that's what's the great thing about the spreadsheet, the matrix. The matrix looks at total project cost, and if you can't save a significant amount of time in ABC, then it doesn't come out with ABC as often, because we're looking to save money in ABC, not just do things quick.
Okay. The next question was, and we'll elaborate on it as we go along. Let's see. Can you go back to your section that shows the bridge, and why was the GRS IBS system used?
Mm-hmm. Well, it was a new technology that we had been looking to use. We have been working with the department and Federal Highway to look at where we could use GRS IBS in the state. We thought it held a lot of promise because of the fact that it was most likely lower cost and more durable, because there are no bridge joints, and we're not using bearings on the bridge. So the key thing with GRS IBS, and most people would agree, that they get nervous about using GRS IBS for a waterway crossing with regard to scour. There are some counties and states that are using GRS IBS for waterway crossings, but most states are saying, well, we're going to walk before we run. We're not going to use GRS IBS for a water crossing. But with that in mind, in Connecticut, we looked at all our projects that have at-grade crossings, where we're crossing one road over another, and we looked to see if GRS IBS makes sense. And we have about 8 projects where this is the case. And so it was this is kind of not experimental, that's a terrible word to use. It was a first-time use of this technology, one of the first bridges in Connecticut. And the first one was designed in-house by the Connecticut DOT for an exit ramp in the town of Tolland, Connecticut. This is the first time it was used. This is the second bridge, I should say, in Connecticut where it was used. So it was just basically experimenting with a new technology to see how it worked. And the results have been very positive for all the structures built to date.
Okay. A bunch of questions on that. Looking at it, do you have piles supporting the invent?
No, we do not. We're fortunate in Connecticut. We have a lot of glacial till. We have many places where we can use shallow foundations. When you get closer to rivers, we almost always go on piles because of scour and sometimes poor soils. But once you get away from the rivers in Connecticut, we have some very dense glacial tills, which are very conducive to shallow foundations. So in theory, you could build, we have considered this, building a pile supported footing, and then building the GRS on top of that. That could be done. But in this particular situation, we had quality soils, so shallow foundation worked.
Okay, and then in the geosynthetic reinforcing, what is that material?
It's typically a fabric. We have a performance specification we include in the project, but it's typically a biaxial fabric that's used, very close spacing, approximately 8 inches on center, which is one of the hallmarks that separates GRS IBS from conventional MSE abutments, which have much wider spacing reinforcements. So the key thing is the difference with GRS IBS is that it's not just supporting vertical load, it's also expanding and contracting with the thermal movement of the bridge. So you need quite a bit more fabric.
Okay, and then normally mechanically stabilized wall, your reinforced fill is like a block. It's rectangular as far back as it goes, and this is stepped.
Yes.
Is that correct?
Yes, that's correct. That's another aspect of GRS IBS where you can design it with these steps where you don't have to have the full, although some people do it that way with a rectangular reinforced zone. Federal Highway had recommended that a step procedure could be used, and we went with that.
It sort of follows a failure surface.
It does make construction easier if you do that.
Yeah, I see that. Okay, and then the next question is, what is the fill material? Is it a graded aggregate, or what? You're using local soil? What do you have for your fill material?
That's a great question. You can use either. What's recommended is open graded material, essentially crushed stone, because it's easier to compact. So we typically specify an open graded material. And typically the compaction is usually 2 or 3 passes of a plate compactor to do an 8-inch lift. So that's the material of choice is open graded material.
Okay, and then I guess because this is all just sort of, I don't know, with the material, and that's why you don't use the approach slabs?
Yeah, the key thing with the approach slab, if we think about this is what you're talking about, one of my favorite subjects. What is the purpose of an approach slab? You asked that question, and the purpose is typically we get settlement behind a bridge abutment. We build a new abutment on an embankment. The embankment's going to settle over time, which is going to lead to a bump at the end of the bridge. When you have a GRS IBS where the entire embankment backfilled is reinforced with fabric, that essentially it's one big integrated, is the key word, integrated system where the approach area is integrated with the substrate, the rest of the abutment, and it all works together as one unit, which is why you do not need approach slabs for these bridges. You don't get that settlement bump at the end of the bridge, which is one of the key features of GRS IBS.
Yeah, it settles together with a bridge.
Right. Yeah, exactly. When you have, good point, Tim. If you have an abutment that's either founded on glacial till or piles, that's not going to settle. But you have an approach embankment that will settle. This here, everything is settling together, which is one thing you have to take into account when you build GRS IBS is you need to build the bridge slightly higher, and because you do get some elastic settlement when you cast the deck. It's not a lot, it's a little bit, so you usually set it about a 1/2 inch to 1 inch higher, and you'll get a little bit of settlement, initial settlement when the deck is cast. Long-term settlement is minimal to 0. So there's a couple little quirks with GRS IBS, but nothing you can't overcome with simple calculations.
Okay. Do you think the decision not to use ABC would have, if you wouldn't have used the abutment here, did that drive it? What do you think?
I think the answer to that, Paul, is it depends on what you ended up doing. If you were not using GRS IBS, it would affect the construction time. It would affect a lot of the factors that go into the matrix. So I can't say off the top of my head it would go ABC or would not go ABC. You'd have to go through the matrix and actually go through the parameters. And the major parameters would be how long would construction be for conventional? How long would construction be for ABC? And depending on the method of ABC you chose, those numbers would vary and change. So it might very well come out as ABC if you went to a different form of ABC, say a precast abutment and versus this GRS IBS.
Okay. Very interesting. Some people may ask, I guess Connecticut DOT has specifications on this type of wall. Is that going to be available?
Well, actually, I'm glad you asked that, Paul, because as I mentioned, the 2018 AASHTO guide specifications for ABC include both design and construction specifications for GRS ABS. So that's a good starting point. And then from there, you can build your own special revisions to actually build these walls. So we have a standard specification we developed with Connecticut DOT, working with their soils and foundations unit, and including the use of wet cast block, which is unusual. Most states do not use wet cast block; they use dry cast block. But we felt it was worth the investment to go with a wet cast block for improved durability. So we do have specifications we developed, but like I said before, the ABC guide spec does include provisions for design and construction. Also, Federal Highway has very detailed manuals both on design and construction of these structures at their website. So if you search FHWA GRS IBS, you will find gobs of good information. And when in doubt, you can contact Federal Highway. They're very cooperative. I'll give credit to them. They really do help designers walk through these designs. And Federal Highway does have construction specifications as well, too.
Okay. That's most of the questions I have on this module. I'm going to ask Ahmed if we've got any that have come in during the question and answers. And he may have a question also. Ahmed?
Yeah, thanks, Paul. As a matter of fact, we don't have any new questions, but I do have a general question since we have time. Have you had any feedback from the contractors in regard to your ABC program? Anything positive or negative, things, could help you change your program?
Yeah, actually, I was going to get into that in the last module, but I'll say it now, and I'm going to say it again later. This is a question that came to us from ABC UTC about a year ago here, and a concern that the contractor community around bridge contractors around the country are having difficulty buying into states' movement into ABC. And my remark there, my initial response was, I don't think we have a problem here in Connecticut, but because the pushback really hasn't come back to me. Occasionally we have requests by contractors to change some elements of an ABC project, maybe cast in place footings versus precasting footings. And sometimes there's been requests for wholesale changes if it works within the shutdown parameters. But that's very small number from the large number of projects we put out. But anyway, we said, well, we're going to check with the Connecticut Construction Industry Association. That's for which many of our bridge contractors are members of. And the message that came back to us was, we have some issues that we want to discuss with ConnDOT, about our specifications, but accelerated bridge construction is not one of them. Our contractors have bought in, and it's not a problem for our contractors, but by and large. So, they had no interest really in spending time talking about this because they're engaged. I'm thinking that they're finding that these projects are now going a lot quicker, and there's probably an opportunity for them to carry more projects than they normally could before with accelerated bridge construction.
Yeah, I'll throw another one in. The one complaint we had on one early SPMT project was one of the, as Tim mentioned, the specifications. It was a disincentive specification that basically said that if Monday morning, if the road was not open, there was a certain value per 15-minute increment, and it didn't have an upset limit. So it basically said, if you went to like 2 o'clock in the afternoon on a Monday, it exceeded the cost of the project. So the contractors complained, rightfully so, that they couldn't get bonding for the project because there was no the downside was infinity. So those are minor issues, and we worked it out. An addendum was put out, that was adjusted, and the project moved forward. So
Right.
as I said, very minor issues. Contractors.
Yeah,
and when
we've adjusted that in our projects. So,
Yeah.
you know, that's not a showstopper. And
Well, yeah, I think the key thing, Tim, is that when issues were brought up by the contractors, the department responded and adjustments were made, and then we moved forward with the program. So
Yeah.
you're always going to have some squawking from contractors. I always say contractors like to cast concrete, but I think more and more, especially these days where it's so hard to find construction personnel, by prefabricating things and reducing the number of workers a typical contractor needs on a project site, I think we're getting more and more buy-in now. They're saying, well, we can build more bridges with fewer workers, and maybe that's an added benefit as we move forward.
Thanks.
I think we're late now.
Marilu, that's all the questions we have.
Thank you, Paul and Ahmed. We're now at the end of the fifth 40-minute module. Thanks again to Mike for presenting the fifth module, and to Mike and Tim for responding to your questions.